Okay, Assalamualaikum warahmatullahi taala wabarakatuh. So today I'm Ahmad Zami bin Shamsuri. So today I'm going to present a COA project. So I used uh, tool 3, which is PassMark performance test. So what is PassMark performance test is PassMark software has that is a robust, commercial grade synthetic benchmarking suite designed to evaluate the raw processing, throughput, and operational efficiency of modern computer subsystem, unlike holistic benchmark that output an abstract single figure performance index. Also, performance test target specific functional hardware units within the processor. Okay, so uh, first thing first, I want to show you how to download the PassMark performance test tools. So this is you can click PassMark product performance this link, and then you will get to this page, or you can search on PassMark performance test. Sorry. Okay, so you click on the top, so will get this page like this, and then what you have to do is we're using a free tools. So this is different option of OS. So Linux, Mac OS, mobile. So I use Windows, then Windows, then the description of the version of performance test. So this is for Intel, AMD, for ARM CPU, for Intel and AMD CPU. So we use the performance test version 11.1 for Intel AMD because I'm using AMD CPU. So we click on download. Also, this is the system requirement. So Windows 11 for ARM, we need 4 gig RAM, ARM CPU, and you have to free up space for this app. So when you're done downloading, you just click this, and then we are running the tools to set up the the tools. So we choose English, and then this is the agreement. So we just accept the agreement and next. So this is where you going to set up the. We're going to put the file destination. So next, then click and install for the extra team. Okay, then you complete. Then this icon will come up in your PC startup. So finish, and then go click this. I suggest you to run as administrator. Click yes. Then the app is ready to run. Okay, so the interface is like this. You can scroll. Yes. So this is part of this motherboard. This is motherboard, and this is CPU, and this RAM, memory disk, GPU. Okay. So wait for the collecting info like this. Okay, so when done, you go to uh, CPU, AMD, this logo, this icon. Okay, so this is my spec, laptop spec. So I'm using AMD Ryzen 5 7000 series. So with 6 cores and 12 threads. So my clock speed is 3294 megahertz. Okay. So also they shown the CPU this and GPU temperatures. So first thing first for workload A, for for workload A, uh, okay, first thing first, I forgot uh these are advantage of using PassMark tools. So it's a granular test acceleration. So it is unlike a blended system benchmark that run mix and uncontrollable code segment. It permits the complete isolation of the CPU suite. So it allows you to engineers to perfectly isolate individual execution variable such as separating scalar ALU to out throughput from vector coprocessor and extension without system interface from disk storage or memory bus bottlenecks. Second is standardized for outputs. So PassMark is calculate metric using a raw structural operational frequencies measured in a million operations per second and compressive cross architecture comparison because the tool provide integrated access to historical data. Disadvantage of using this synthetic first is synthetic workload optimization. The core processing loops utilize highly repetitive and mathematically pure instruction sequences because the tiny data loops are heavily optimized. They frequently fit completely inside the processor high speed L1 or L2 message lines. And then second one is operating system overhead interference. PassMark performance execute entirely within the user space layer of the Windows operating system because PassMark does not run natively on bare metal. Bare metal. Its execution threads are subject to ongoing interpretation from OS thread scheduler, background, service daemons, and asynchronous hardware interrupts. So the last is physical hardware abstractions. Okay, so um, the task is in this project is first here. Okay, so workload A. So workload A, we specifies operational matrices detail and how students should set up their tools, execute workloads, track architectural performance parameters, and extract data, compute fundamental computer organization and architecture metrics. So workload A, what is actually it is measure core part length throughout via the execution of fundamental integral operation, standard floating integer operation, standard floating point, and data sorting algorithm. Okay. So to calculate as MIPS operation, MIPS, it is a million instruction per second. So in mathematical, we like this one, operation per second over 10 power of 6. We also need to calculate the cycles per instruction, CPI. So it's connected with MIPS, which is the CPI need CPU clock speed over the MIPS. As I shown before, my my PC processor using I have the Ryzen 5 and my clock speed is 3294 megahertz. Actually, the formula need to be in megahertz. So this is the data that we get from these tools. So this is I run before this test. So this is for just example value. So you go to CPU mark and then there is tabs which is integer mat, floating point mat, and also sorting because the fundamental of it doing the workload A, we just need to read the value of integer mat, floating point, and the sorting algorithm. So we just click on the run. So wait for it. So this is my result value for 48,695. So but you can see this MOPS, the apps is shown the value in MOPS per second uh, unit. So next is floating point. 27,585. So the floating. Wait for the running. Okay, this is my value, and the graph is shown that my CPU versus the world CPU, which is these two is showing the benchmark. So my CPU is between mid-range 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 laptop mid-range CPU. So this is high-end, very a few. Okay. So then I put the value. Sorry. MOPS. So the MOPS, we use the value MIPS, and then my CPU clock speed shown 3290.9 megahertz. And then this is the CPI, cycle per instruction, so integer mat. So we divide, and this my result. So for ISA structural bottlenecks, uh, so the impact is CPU execution pipelines like the integer ALU are fully occupied, or if the instruction fetch or decode units cannot supply instruction fast enough, the processor stops. This hardware limitation prevent your CPU from processing more data, capping your MIPS for at a lower limit. So CPI estimate how many clocks cycles it takes to complete a single instruction. Ideally, modern superscalar CPU on a CPI well below 1, meaning they finish multiple instructions per cycle. So when a structure bottleneck occurs, such as two instruction fighting to use the exact same multiplier unit at the exact same time, one instruction must wait. So this hardware conflict delays execution, wasting clock cycles, and directly causing your estimated CPI value to climb higher. Okay. So next, to show you I think I have mentioned the details of workload B first. So it provides another architecture angle that reflects the current modern computer processor For example, single instruction, multiple data. This is the example. And memory hierarchy, structure coherence. So AVX 512 is an incredibly powerful SIMD extension designed by Intel for 86 64-bit architecture processors. ARM Neon is the foundation SIMD hardware engine designed for ARM architecture processor, powerful smartphones, tablets, Apple Silicon Max, and low power IoT devices. So probably what it wants is shift focus from standard pipeline throughout to advanced vector extension and floating point unit FPU saturation. The benchmark is reconfigured to bypass standard data structures and target wide registers such as Intel, AMD, and so on. Modern processors use single instruction, multiple data, SIMD, to execute a single mathematical operation across a wide vector register packed with multiple data. So we use a vector metric component and observe architectural performance value data. So vector metric component, uh, we use vector map, or in this app there's no vector because it use wait we run again. So we use a floating point, and the extended instruction SSE, which is a vector map. They reading my CPU information. So this is the value. Okay, it isolate advanced vector processing capabilities, as you can see on the screen, just before, and this value. So, so in PassMark, score represent our vector metro output instead of traditional scalar pipelines that handle data one pair at a time. So this test saturates wide hardware SMMD registers by feeding packed data streams into the CPU simultaneously. Instruction, fetch, and decode overheads are minimized, resulting in a massive surge in raw operational throughput. So this is the flowchart for the A. So start and then so on. How to write the app. Then this is for flowchart for workload B. Okay. Yes. And then this is the analysis of workload A. So as you can see, it's very too long, the analysis. So basically, uh, this exposes server structure bottleneck, certain relies on the heavy conditional loops that completely stress the branch prediction unit. Then micro architecturally, CPI well below one prove that our processor is operating in a superscalar mode, executing multiple instructions simultaneously across parallel LLCs. Then for the workload B, instead of traditional scalar pipelines that handle data in one path, as I said just before. So these tests are scheduled wide and hardware SMID register. by feeding packet data streams into the CPU simultaneously. Instruction fetch and decode overheads um, minimized, resulting in a massive surge in raw operational throughput. So to conclude, the benefit is component level metric isolation, granular low level subtask selection, direct operational mapping to COA metric. Limitation is this through synthetic execution loop over optimization. Second is user space, software interface overheads, and the third one is abstraction of architectural indicators. Okay, so the conclusion is the implementation of PassMark performance test successfully provide empirical validation for performance architecture theories through the two distinct workloads, workload A and workload B, isolating basic math and sorting routines, highlighted how the CPU handles instruction lanes. So next is restricting the weight match to floating and SSE allow us to directly analyze vectors relation rather than executing simple scalar instruction. The application successfully saturated the processor YSMID vector register by feeding the packet data stream simultaneous the CPU minimize instruction. So this is the for result of analysis of workload B. And then from point of view of in a professional level, utilizing PassMark bridge the gap between abstract textbook concept and physical hardware behavior. So seeing a software sorting loop, you get structural metrics provide a real world proof of pipeline, stores and branch penalty. We also develop critical diagnostic skills by learning to account for user space noise such as Windows operating system thread, scheduling, and background interrupt which introduce minor variance and requires running multiple test iterations to ensure the reliable uh, baseline. Okay, so that's all. That's all from me. I'm Azam Subsidy. So thank you for watching. Thank you for giving me time to watch me present. Yeah.